Hey there. So you've probably memorized the formula. Displacement equals velocity times time. We've all done it. But what if I told you there's a way to literally see that equation in action, just by looking at a graph? Today, we're diving into what I call the area story. It's this awesome visual tool that can turn really complex motion problems into, well, simple geometry. By the end of this, you won't just know the rule, you're going to understand exactly why it works.
So here's our roadmap for today. We're going to start super simple, with a basic trip at a constant speed. Then, we'll crank it up a notch and see how acceleration changes the picture. After that, we'll look at a full journey, with forward and backward motion, and uncover the one universal rule that ties it all together. And finally, we'll show you how to add this powerful concept to your physics toolkit.
All right, first things first, let's do a quick refresh on our star player for today, displacement. Now remember, this isn't just about how far you've traveled, right? It's about the change in your position from your starting point to your ending point. That little detail about direction is absolutely crucial, and you're about to see exactly why. Okay, let's ease into this. We'll start with the most straightforward scenario you can possibly imagine. An object just cruising along at a nice, steady, constant velocity. You know this concept inside and out, but let's take a look at what it actually looks like visually.
I bet you've used this formula a million times. Displacement equals velocity multiplied by time. It's pretty much the bedrock of kinematics. But today, we're not just going to use the formula. We're going to see what it looks like as a picture. And trust me, that's where the magic really happens.
So let's plot this trip out on a velocity-time graph. We've got velocity up the side, on the vertical axis, and time running along the bottom on the horizontal. Our velocity is a constant 10 meters per second for the whole 5 seconds, so what does our graph look like? Yep, just a simple, flat, horizontal line.
Now take a look at the shape that's formed between our velocity line and the axes. It's a perfect rectangle, right? Well, that is no coincidence. The geometry of this very simple shape is about to unlock a massive physics concept. So let me ask you, what do you think the area of that rectangle represents?
And boom, here's the big reveal. On the left, let's do the simple geometry. The area of a rectangle is just base times height. That's 5 seconds times 10 meters per second, which gives us 50 meters. Now look at the right. Let's do the physics. Displacement equals velocity times time, which is also 50 meters. They're exactly the same. The area under the velocity time graph is the displacement. It's that simple and that powerful.
Okay, that works great for a steady speed. But come on, when are things ever that steady? What happens when our object starts to speed up? Let's take a look at a trip with constant acceleration.
Right, so with constant acceleration, our velocity is climbing at a steady pace. That means our graph isn't a flat line anymore. Now it's a straight upward sloping line. And the area underneath this new line, well, it forms a trapezoid.
Now, you could go dust off the formula for the area of a trapezoid if you really want to, but honestly, there's a much easier way. Let's just break it down into shapes we already know and love. You can see a rectangle on the bottom. That's kind of like our starting velocity. And then there's a triangle sitting right on top, which represents the boost in velocity from the acceleration.
So let's imagine our object started at 10 meters per second, and then it accelerated for 5 seconds, ending up at 20 meters per second. The bottom rectangle's area? That's just 10 times 5, which is 50 meters. Easy. The triangle on top has a base of 5 and a height of 10, so its area is 1/2 base times height, which is 25 meters. So what's the total? 50 plus 25? We get a total displacement of 75 meters. See? The area method works perfectly, even with acceleration.
All right, things are about to get even more interesting. You know, real-world journeys aren't always just in one direction. What happens on our graph when an object slows down, maybe even stops, and starts heading back the other way?
So far, all our velocity has been positive, right? Everything's been above that horizontal axis. But look at this graph. The line actually dips below the axis. That means we have a negative velocity. Our object is moving backward. So what on earth does that mean for the area in that section?
And this is the other crucial piece of the puzzle. Any area that's above the axis is positive displacement. But any area below the axis, that represents negative displacement. This graphical method is so cool because it automatically takes care of the vector nature of displacement. It keeps track of the direction for us.
So, to find the total displacement for the whole trip, we just add up the areas from each segment, keeping our new rule in mind. That first triangle gives us a positive 10 meters. The rectangle adds another positive 20. But that final piece is below the axis, so we subtract its area of 5 meters. What's the final displacement?
10 plus 20 minus 5 is 25 meters from where it started.
So we've handled rectangles for constant velocity and triangles for constant acceleration. But what happens if the acceleration isn't uniform? What if the graph is a curve?
And this is where this concept becomes a real superpower. I mean, think about it. Real-world motion is almost never perfectly constant acceleration. You get curves. But even when we can't use our simple geometry formulas, the physical meaning of the area between that curve and the axis stays exactly the same.
This is the universal rule. I want you to burn this into your brain. It doesn't matter if the shape is a nice, neat rectangle, a triangle, or some wacky, complex curve that you'd need calculus to figure out. The area between the line and the time axis will always represent the object's displacement. It's the unbreakable link between the graph and the actual motion.
Okay, let's bring it all home. Let's talk about why this isn't just some neat little party trick. This is an essential tool you absolutely need in your toolkit, especially if you're getting ready for something like the AP Physics 1 exam.
So, why does all this matter? Because the area story is your secret weapon. When a problem throws a complex motion graph at you, you don't have to panic and frantically search for the right kinematics equation. You can just look at it, break it into shapes, and find the answer. It lets you handle changes in direction without even thinking about it. You're basically turning a messy physics problem into a simple geometry puzzle. And hey, you've just accidentally built the entire foundation for understanding integration and calculus. Not bad, right?
And that leaves us with one final thought to chew on. We've totally mastered what the area under this graph tells us. So, what about the other major feature of a line on a graph? What physical quantity do you think the slope of this very same graph represents? Think about it, and we'll catch you next time.